My name is Elias, and I'm a PhD student at the Royal Institute of Technology in Stockholm, and I'm working in a research field called industrial ecology, where we are basically studying the material and energy flows across our societies. And I apply various methods to study more specifically biochar systems. And I gave a talk, webinar 2 years ago here, and I was presenting my conclusions so far for my PhD, and my last slide was actually this one, where I was telling to the audience that, well, biochar systems in Sweden have quite good, they have a good potential, but we need to make sure that these biochar systems achieve tangible benefits when we use a biochar beyond just the carbon sequestration. And at the time, 2 years ago, biochar use was still quite emerging, and we didn't have really good assessments of the use effects of biochar in the products we have here in Sweden. And so that's what we did over the past 2 years. We really looked into urban applications of biochar. And I'm gonna present to you today both life cycle assessment results, so climate impacts and so on, and also then later on a case study for a city in Sweden called Uppsala, and trying to estimate how much biochar they could be using in that district. So let's start with the first part, which is a life cycle assessment. So for those who know Sweden and the biochar history in Sweden, you probably know that the first time biochar was used was actually for planting trees in Stockholm. That dates back to 2012. And so here in Sweden, use of biochar is mostly located in urban areas, not really in the agricultural sector. So we can say that the market, the urban market is the most developed one, with some products that reach a high commercial readiness level, while other products for urban areas are being developed today. And so several questions arise from this for us, for life cycle analysts. And the first one is that, well, these biochar products are supposed to replace other materials, other products. And how does the environmental footprint of these two products, biochar and reference, compare? Are there any environmental burden shifts between them? We'll look into this. Then you also know that biochar can be produced from different biomass in different reactors, and that in the end they have different properties. And we are wondering how these differences in biochar supply chain can affect the footprint of a product. We also looked into that. And then last question we had is this common critique that is made to biochar use as a carbon sequestration. Some people argue that it could actually be used for producing fossil-free steel if we would burn this biochar. And so the question that is actually behind there is, what is the most climate-smart use of the biomass or the biochar? How can we do such a comparison? So in this study, we have modeled 5 biochar applications that you see here. So tree planting, which is the first application in Sweden. So where we have a tree that is replanted in what we call a constructed soil layers with biochar and rocks mixed together. Then we have extensive green roofs that can be used to cover buildings in urban areas. And the particularity here is that we have a mineral soil that contains a little bit of biochar. Then we looked also at a very common product like landscaping soil, quite extensively used in both private gardens and landscaping projects, so with and without biochar. And also concrete elements are currently being developed in Stockholm. So concrete with a certain fraction of biochar. And this is not used for buildings, but it's for now at least allowed to be used, for instance, for tree pits and also decorative pavement stones. And the 5th application we looked at is in the water treatment sector, the option to use biochar as a carrier for drinking water treatment, a pre-treatment step where we would remove BOD, so carbon basically in the water. What you may note is that these products are at different technology readiness level, and that for every product there are of course various possible designs and recipes, but we had to pick one and then make environmental comparisons. There was also another product that we looked into, which is of course the oxidative use of the biochar. What if we burn the biochar to produce pig iron? Pig iron is actually the precursor in the steel production process. Then we looked at different biochar supply chains, and these biochar supply chains we had 4 different biomass types, going from wood pellets, garden waste, logging residues from Swedish forest, or willow produced on agricultural land. And all these biomass were assumed to be converted in also different kind of reactors. So we took 3 reactors that exist in Sweden as syngas heated reactors, similar to what Pyreg and Biomass can produce, electricity heated reactors like the one from Biogreen, and also these mobile units coming from Australia. What is important to know here is that we had, for an LCA perspective, we have to make assumptions on the reference land use or biomass use. In all cases, we have set the biochar yield to 25%. These reactors are producing different amount of district heat as a co-product from the biochar production. And of course, the biochar that we get here, they have different properties, both in terms of carbon content and bulk density. And when it comes to the biochar stability, we have assumed that it would only depend on the final application. And if it was a soil application, we assume 80%. If it was a concrete application, then we assume 95%. So we didn't model all the combinations between these 4 biomass types and 3 reactor types, but we selected the 7 most relevant ones for us. What I want to stress here is that these different supply chains, the key differences are the carbon content that could vary between 93% carbon down to 70% for the garden waste. But we also had very different bulk densities from 200 kilogram per cubic meter up to 500. And there are also some differences in how much electricity and heat is produced between the different reactors. That's a variability we wanted to investigate. And last but not least, the energy system in life cycle assessment plays usually a big role in the assessment, in what the footprint of your product will be. So we did the modeling with 2 energy systems. The Swedish average conditions, where heat, electricity, and transport fuel come respectively from wood chips, an average mix that is rather decarbonized for electricity, and a mix of diesel and biofuel for transportation. And we also had all our results available with a different energy system, if basically based on natural gas and diesel. But today I will be mostly presenting the results in the Swedish average energy system. So let's go now into the first set of results that we have, which is the impact from the production of the biochar process. So what we call the cradle-to-gate. And for that, I need to show you a flow chart of what was included in the assessment. And well, so the biochar production starts with the supply of the biomass, and that differs between the different biomass types we have. Then we have the step where we have the drying and the pyrolysis of the raw biomass, and that includes here the manufacturing of the reactor, the electricity use, but also direct emissions of air pollutants during the process. And of course, we get from that the biochar. But we also have the co-product, the syngas, that we're assumed here to be burnt directly on site to generate district heat. And that district heat is then assumed to displace to avoid production from another source. And to be complete, an LCA always needs to assume a reference land or biomass use, so that we also included here. And how does it look like in numbers? So on this graph, you can see the 7 different biochar types. So from wood pellets up to logging residues and willow. And on the vertical axis, you have, of course, the climate impact is expressed in kilograms of CO2 equivalent per ton of biochar. And the different colors in the bars represent the different steps in the life cycle. And what we can see here, roughly, is that the impacts related to production, if we exclude the carbon sequestration term, were in the range of 700 down to 300 kilograms per ton of biochar for most of the supply chain. And then we have a negative value here of around -1,000 for the willow. And that's a special case, and it's due to the fact that the willow, when you cultivate it, you actually increase the stock of carbon in the agricultural soil, and that is represented here. We also see that the differences in transport distances between type of biomass don't really play a big role, and that the impact of producing the reactor is really barely visible on this figure. And last comment would be here the difference between the willow, which is a cultivated biomass that has use of fertilizer in quite large amounts that leads to high emissions here, compared to the other biomass, which are mostly residues, which have a much lower footprint, if you look at this column here. Right, but this is per ton of biochar. And most people actually who work with biochar, they usually express or consume it in volume units, so in cubic meters. And that's what we have on this figure, so per cubic meter. And while the net score was roughly similar here across supply chains when we look at it per mass, when we add into it the bulk density of the material, then we start to see more significant differences between the biochar. And the most dense biochar, the wood pellets, have a much higher carbon sequestration term than the other types of biochars here. The other ones, the woody ones that are not pellets. So this is important to bear in mind, that when you are actually using biochar in a soil product, depending on the biochar you have, the embodied carbon sink will be very different. So the conclusion that we have, we want to, at this stage, the first conclusions are that biochar carbon sink can vary significantly when we look at it per volume. And here we had a factor 3 between wood pellets and garden waste. I didn't show you the figure in the fossil energy system, but the conclusion is that if you are if your electricity source and your heat source are natural gas or anything worse than that, like coal or oil, it wouldn't be climate smart at all to produce biochar. You would have more climate benefits from substituting and burning fully the biomass and substituting more of these fossil fuels. And the order of magnitude here we have is that producing 1 ton of biochar is between 300 to 700 kilogram CO2 equivalent per ton. So now let's go into the second set of results, and this is looking at the biochar products. So we had these flow charts where we were producing a given amount of biochar, and now we are going to use it to manufacture a product. So we have to add another step, the manufacturing of a product, which consumes other materials. And then for a life cycle to be complete, we need to include the use phase of the product and its disposal. And here the unit that we are using to analyze a product is 1 amount of product. And you remember that we had 6 products, starting with tree planting, and I have detailed slides for all of them. But because I'm quite limited in time, I will not show you all the details. We'll go to a more synthetic version. So remember these 6 products. I can tell you that for tree planting, we have about 1,000 liters of biochar per tree that occupy a root volume of 15 cubic meters. And that covers approximately 10 square meters of road. And in that tree planting technique, the biochar is mixed with macadam and replaces a conventional soil mix. For the extensive green roofs, there the biochar content was about a bit less than 1 liter of biochar per square meter of roof. And the main difference between the reference and the biochar product is the composition of this mineral soil layer here that you have in brown. But also during the use phase of these roofs, the manufacturer recommends to use less fertilizer in the biochar kind of roof than in the reference one. The planting soil had a biochar content of around 140 liters per cubic meter. And there we had a mix of biochar compost that is actually replacing fully the peat content of this landscaping soil. For charcrete, instead of being measured in volume, it's a mass content of biochar that is important here. And we had about 100 kilograms of biochar per cubic meter. And we have tested several hundreds of recipes, but I'm only going to present the results for one of these recipes. For the water treatment step with biochar, the requirement is about 15 liters of biochar per 1,000 cubic meters of water treated. And the biochar is replacing a plastic carrier that you can see on this picture. It's very conventional in water treatment operations to use these filters. And for the steel, the amount of biochar used per kilogram of pig iron was defined by the energy and the carbon content of the biochar. And it was assumed to replace hard coal and coke. So that's a quick overview of how we modeled the different life cycles. And we have now figures about the climate impact. And here you see the first 3 applications, so tree planting, roof, and landscaping soil. You see also the 7 biochar supply chains, and also the reference product here, the last column. And of course, we have the climate impact still expressed in kilograms of CO2 equivalent. And what we can say for these soil applications, in all cases, we had a biochar product that had a lower climate impact than the reference one, even without accounting for the carbon sink. But you have to look at the dots, which are all lower than the black cross in this one. And of course, when we include the carbon sink in the assessment, we get even better results. The impact reduction between the reference and the biochar products is actually mainly due to the substitution of peat. And that's what we can see really well in the landscaping soil case, where we have when we have a lot of, you see the red bar here is basically the impact due to peat use, which nearly disappears when we replace it fully by compost and biochar. The fraction is due to mostly sand. And we can also again see that there is a large difference between the supply chains in terms of how much carbon sink is embodied in the product. So you can here again see between the wood pellet and the other ones. Now looking at the other set of products, which are charcrete, biofilm, and pig iron, we have again the same conclusion that, well, not exactly the same conclusions, in fact. For the charcrete, we see that if the carbon sink is not included into the assessment, the net impact of the biochar concrete is much higher than the one of the reference. And this is due to the recipe that was designed that had a higher cement content than the reference concrete. And so the company developing this charcrete is actually working on other recipes to improve the product. Water filters then had always lower impact than the reference product, and that's here due to the replacement of fossil plastic that has a high impact at production, but also a high impact during the disposal phase of it, which is incineration of plastic. And for steel, we can simply say that using the coal, the biochar, instead of hard coal and coke, reduced impact of the steel by approximately half, but we still have other impacts still remaining. It's not neutral because we're using biochar. Right, so that was a brief overview of the LCA results, the comparative results. We can go more in detail if you have questions about each product. But still, so far, we cannot make any comparison between tree planting and the use in steel making, right? Because these figures don't have the same units. So for that, we need to work a bit more and expand a bit this flowchart. So the thing we have to do is find a common unit. And for that, we need to add the reference product, account it as an avoided burden, and then measure all our impacts for 1 ton of biochar being produced and used. And that looks like this on this figure. So here we have the wood pellet biochar and the 6 different applications. And the horizontal axis is measured in tons of CO2 equivalent per ton of biochar produced and used. And how to read the value here is explained there. So if the net value is below 0, it means that using biochar for that application is going to give you net greenhouse gas emission reductions for what we want. And if it's above 0, if the net value is above, then we actually increase our emissions compared to the reference state we are in. And so what we see here is that for all products, when we include the carbon sink, we have a negative result, which is what we want. We have a net savings of greenhouse gas emissions, and but for that we need to account for the carbon sink. If we don't account for the carbon sink, it will kind of depend on the product if it's an improvement or not. Then when I look at another supply chain, so if I look here at garden waste instead of wood pellets, we have this rather same conclusions, but you will notice that the benefits from substitutions of other materials, so the orange bar, they are twice as big as in the wood pellet case. And this is because here we're looking at 1 ton of biochar. And indeed, 1 ton of biochar, if it's garden waste, it means 2 times more volume than for the wood pellets, because it's less dense. And it means also that you will plant twice as many trees with the same mass of biochar. So that's why all the benefits are increased here. Yeah. So, and since we wanted to compare these biochar uses with pig iron, with steel making, that's the last statement I make here, that all the biochar application can outperform in terms of climate change benefits the use in steel. But for that to be true, we need to have substitution of other materials like peat and plastic, and we need to have a guarantee that the biochar stability will be high. And here we have above 80% assumed for cases. So that was it for the climate assessment of our systems. Now we also had in our study other environmental impact. Everything is not just about climate change. We have also impacts in terms of resource use, human toxicity, and ecotoxicity. And here the picture is much more complex. I will not go at all in the details of it. It's not as straightforward for the climate. And we see that actually the biochar products can have both higher and lower environmental impacts than the reference products. And what determines this difference is really the type of biomass you're using, the production process of your biochar, and also what materials you're substituting. That really controls whether or not you will have other environmental impacts that are worse or better than the reference. So that's the end of the first part of my presentation for the LCA. And that summarizes here all the findings we had so far. To save time, I will not just read through them. So the second part of our study, as I said, was more a material flow analysis. And we applied that to a city called Uppsala and the new city district that they are building. So this district, we call it SÖS. They are planning to build it now in the coming decades. And it's going to host about 60,000 inhabitants. And the question we have, or the question the municipality had is, how much biochar can we use in that urban environment? And so we tried to estimate that for them. And we took again this 5 urban applications. And we assumed that for the trees, the trees would be planted along the 50 kilometers of road with 10-meter spacing between each tree and on both sides of the road. And after discussion with entrepreneurs who do this kind of construction, we understood that the lifetime of this constructed soil was probably going to be around 50 years before it needs to be renovated. For the green roof, we assumed that half of the roof area would be covered with biochar roofs, and the rest would be used for PV panels. Landscaping soil was assumed to be used in all the public parks and also the residential areas where they have gardens at different rates. Concrete was only assumed to be used for the tree planting and also to some extent for decoration of gardens, with some tiles being spread around. Water treatment, we estimated the biochar demand at the district level using water consumption statistics. And yeah, that's about it. You have to note that here, depending on the type of biomass we're using, since density changes, the total amount for the district will depend on the biomass type. And to solve these kind of systems, we use a method called stock-driven dynamic material flows. So, looking at the results, biochar demand. So we estimated that during the construction of the district, the demand of biochar would be around 40,000 cubic meters. And that is here for the construction phase, so spread over around 25 years. And after these 25 years of construction, the demand would drop and only be re-increased again in the future when we start to do renovation of the tree planting and also maybe the roof, the green roofs. You also see that most of the biochar is actually consumed for the landscaping soil application and the tree planting, while green roof, water filter, and concrete only contribute marginally to the total demand. In terms of biomass consumption, we had a range here. So doing that, for building this district with a lot of biochar would require between 86,000 tons down to 34,000 tons of biochar. And we compared this to different statistics we have in Sweden. So for wood pellets, it would mean 7% of 2020's annual production and consumption of wood pellets to be used. The garden waste amount that is needed here for the construction is actually roughly equal to the total garden waste generated in the entire municipality of Uppsala. That's quite an interesting order of magnitude. In terms of logging residues, if we were to do it with logging residues, we would require about 70,000 hectares of forest land at final felling. And for willow, we would have to cultivate about 800 hectares of willow for 25 years to get that biochar, the biochar we need. Second last slide, we have here the biochar end of life. It's the next step, what we get. So the biochar is actually blended with other materials, and when the product reach end of life, this flow needs to be managed. And so we were willing to know when it would need to be managed and how much. And this material flow analysis tells us it would be mostly in the second half of the century that the municipality would have to deal with this secondary flow of biochar. So at the end of the study period, we also illustrated that at the end of the century, basically, we would have about 60% of the biochar that would remain in the parks, 20% that would still be in use in the buildings, in the roofs, in the tree structure, and that also nearly 23% would be accumulating in landfills. That's an insight here. It raises some questions on how do we manage that end of life flow and what do we do about it in 100 years. And so finally, we also estimate from that the total amount of carbon dioxide removed from the atmosphere. And so the flow per year is depending on the biochar you have, it's between 800 to 2,400 tons of CO2 equivalent per year that would be sequestered over the construction time. And this can be compared to, for instance, the expected emissions that would arise from building this district, and the city has estimates that building the city this new part of the city would cost 20,000 tons of CO2 per year. So you see that it's like roughly 10% that could be abated through this. And currently, the total emissions of the municipality are estimated around 1 million tons of CO2. So we see that it's not going to offset everything we're doing. So with this said, I have maybe a few more minutes for final word. The recommendation we have, the design recommendation we give now to people who develop biochar products is that your product should have a better environmental performance than the current products you're using, even if you don't account for carbon sink. And there are several reasons behind that. When it comes to tangible benefits for carbon dioxide removal, in this study, they were mainly related to peat substitution and plastic substitution. And when it comes to biochar supply chain variability, we think that it's important for producers and for product manufacturer to really document the type of biomass conversion process and biochar properties they get, but also the mass and volume contents of their products. And finally, at the city scale, when we take a look at an entire district, we saw that large amount of biomass will be needed if we want to use biochar in all urban applications, and the local garden waste is unlikely to be fully enough if we really insist on using biochar. And at the same time, biochar carbon sequestration might just be in the end equivalent to a couple of % of our current emissions. So we need also to work on reducing our other emissions, not just rely on compensation. And I think I will finish on that word. Thank you for listening. And I'm not alone working on this. I have also my supervisors, Eric and Cecilia. And if you want to have an overview of all our previous work, you can look into these links here.
Thank you very much, Elias. Always really interesting to see CA studies on biochar, and what we think we're doing is sometimes not what we're actually trying to do. So for everyone, if you have any questions, please write them in the chat, or you can unmute yourself and ask directly to Elias. And I have one question now that came up. So you said biochar is mostly the biggest impact if you substitute a material such as plastic or peat. What do you think? Is it also true if you don't use wood, for example, but use the feedstock as a substitute? So, for example, sewage sludge, which would substitute the removal costs of that.
So sewage sludge is a very particular feedstock. We didn't work with it, but indeed, sewage sludge, the current management of sewage sludge is probably not optimal, and maybe pyrolysis of it is a better alternative. But then there are also some discussions regarding sewage sludge biochar, with the carbon content of it being also much lower. We're not really sure about the stability of it in the long term. But I generally agree with this statement from the person who asked, that it's probably a good way to deal with sewage sludge as a treatment option using pyrolysis. Yeah, and these benefits would be indeed quite interesting. But they were out of the scope of our study here. But I agree.
Quite a comprehensive study already. So Andre was asking, biochar made from combination feedstocks, biomass, municipal waste, plastics, rubbers, as well as contaminated biomass, can be scaled up and will sequester. Okay, that was another question, sorry. Was there evaluation of the differential created by converting the biomass into pellets before pyrolysis, or having the biochar processed into pellets?
No, we didn't compare that, because the main reason because we didn't do it is because we know here about we have two companies here in Sweden that are buying wood pellets and then producing the biochar with it, but we didn't really compare if we have to do the difference between pelletizing before and after. The main difference, when you use pellets from a life cycle perspective, the difference is that you're going to use energy for doing the pellet, right? That's why actually pellets have a higher impact, if you remember one of the slides here, than the other feedstocks. So if you tell me that you're going to use less energy if you do the pelletization process after, then probably you would have a slightly reduced impact for production at the production stage. But it might not be such a big difference. You would still be in that order of magnitude that I gave, between 300 to 700 kilograms CO2 per ton of material, per ton of biochar, would be in that order of magnitude still.
And then Tony had a question. So as we found the biochar after several thousands of years in the soil, do you think it's still necessary to apply the precautionary principle about biochar stability?
Indeed. So stability of biochar is an extremely complex topic. I still think it is important to talk about, to have a precautionary approach when we talk about it. I know what has been said in literature. I've been reading a lot about biochar stability. I could show you this slide. It's unfortunately in Swedish. But if I pick up a few lines here, is that in my opinion, and I've been reading a lot about biochar stability in the last years, the true answer to how stable is biochar is it will depend, it's uncertain, and we will never know with certainty in our lifetime. And that's a quote from one of my supervisors, who is a soil scientist, let's say. But of course, we need to give a political answer because we are using biochar and we hope it will be a good carbon dioxide removal technology. It's true, as a person said, that in the literature, we have people who wrote that it can stay in the soil for several thousand years, several hundred years, but we have also results where it was shown that it would totally be gone after decades. So the key message here is that it actually depends. There is not a single value for biochar stability. But what we are also sure is that biochar stays longer in the soil than the parent biomass it has been produced from. I can also show you these numbers. So I've collected data from various papers, and here it's like the experimental measurements that have been made. The longest lab experiment is here, 10 years, and we had, after 10 years, 5% that were gone. Then we have also here this experiment here, where it's a gasification biochar at 1,200 degrees, and you see that after 2-3 years, you have 85% remaining. Right? And we usually do extrapolation of these curves to get the 100-year value. And so that's what it looks like. And you can see that I have all range here from, so that's a raw biomass, the under curve. And after a couple of years, we don't have anything left. And we have also some experiments. This was in a water clogged field that we had a lot remaining. And we have also the gasification where there is nothing remaining after 100 years. So there is a whole range of values. It's not that simple to say it's going to be thousands of years. I disagree with the oversimplifying it. We still need to understand better how it works.
Okay, great, Elias.
I'm sorry, just a stupid question. You have used the term like 15-liter biochar. How you are measuring it in liters, because generally we measure in mass terms like kilograms.
For which application? For the
water? For soil application, soil and water both.
Yeah, but actually, when I do my assessments, of course, as a life cycle analyst, I use mass. Of course, I know the exact mass amounts. But in fact, when you do soil applications, the companies who develop here soil products with biochar, they give you the recipe of their soil in volume, and they tell you, well, my soil has a 20% volume content of biochar, but you don't really know what density of the biochar it is. And that's what we wanted to illustrate with this kind of study. So yeah, there is a mass behind, but actually volume is important. And for water treatment, we have seen that biochars with different bulk densities have achieved the same BOD removal efficiencies. So that's why we had a volume content as well for the BOD removal. And not the same mass. Yeah.
So just as a rough idea, for 1,000 liter of water, how much biochar is needed in terms of, if you say in terms of kilograms?
So here it was 15 liters, and then depending on the bulk density, you take 15 liters multiplied by these ones, you get the mass amount. So it was a couple of, no, not, my eyes are not good enough to make that calculation live, but
Okay.
15 liters
anyway, we have to stop now. So
yeah.
for it will depend a lot on the water you want to treat anyway.
Also, yeah.
So let's go to the, thank you.